Hi everyone, welcome back to the next lesson in our ongoing project example. In this lesson, we're going to be looking at our alarms and building alarms via this structured approach. Now, this is quite difficult to demonstrate, especially the management side of alarms, because every sort of PLC has its own method of management. Everyone else sort of has their own method of coding the logic. So I'm not going to focus too much on sort of alarm configuration and all that stuff for Codesys, because it's not really relevant for the structured approach. But I will focus on sort of how we're setting up this environment. So I'll start by going back to our program and our inlet system and our first manager, which was the switch that we looked at in a previous lesson, and having a look at this alarm index here. So if I open it and have a look at where alarm index comes into our function block, we find that alarm index comes in here and is passed to our global alarm manager. Now, the global alarm manager is a dedicated manager for our structured alarm data. So you'll find here that we have our alarm group, which again is a structure, and it's passed via inout, so via the reference method or pointer method. And then our alarm management is exactly the same, a DUT, and passed via the inout interface. Now, the thing to remember is that this global alarm manager doesn't care about the asset it's in, as in a switch or a pump, or if it's outside of a pump, it can be used anywhere in the project as long as it has a reference to the alarm group that it's controlling, the alarm index that is indexing the alarm group in, because the alarm group is an array. We'll have a look at these structures in a second, and it has its management. And then it's got a condition which sets the alarm on, and an option to say it's a warning for some SCADA sort of visualization display. So let's have a look at the structures around this alarm system. So if I come and look at my structure objects and I look at alarms, you'll see our two alarm group and management. So alarm group, DUT alarm group, and alarm management, DUT alarm management. So this is quite a big structure in terms of what's happening. So I have a alarm active array, which is 0 to 2048, which is 64 double words. And I have another one for my alarm accepted status. And then I also have an array the same length of usint, which holds a status. This doesn't generally get used. It's more for systems that want a diagnostic page where they can see all of the alarms and exactly what status they're in. So waiting for accept, has been accepted, but the condition is still active. This status can hold that information as a numerical value for a text list or something to be shown on SCADA. So the way this system is working is there is 2047 available alarms. We don't use element 0 because element 0 is reserved to tell the system that the alarm is not configured. And then what we do is we pass into our manager, so the switch manager, for example, we pass in a index value which tells the global alarm system which value to be indexing on these arrays. So if I wanted to look at alarm 1, I would pass a 1 in, and the 1 on this array, element 1 would be indexed, and we'd have a look at managing the alarm in slot 1 of the array. If I go back and have a look at the alarm management, these are all the things to do with managing an alarm. So we have some things like new alarm raised, our accept single buttons from SCADA. So it means that SCADA's tried to accept a single alarm that is highlighted in its alarm manager. accept all for accepting all current alarms, and the reset accepted alarms for resetting accepted alarms. These are all used in the process of operators accepting, resetting, clearing alarms off of the system. So if we go back to our switch manager and we have a look inside the global alarm manager, it's fairly simple. There's not an awful lot going on in here. We have a few indirect addressing switches are looking up on index, which you can see places like this. So in our alarm group, if the alarm accepted index is true, it forms part of a reset system. If I go online, this might be a bit easier to sort of visualize. So we're looking at the moment online at index 1 of our alarm system arrays, which is currently not active, so we don't see any of this in an active state. So what we're doing here is we're checking that we actually have an index set. If the index is 0, we simply exit this block and we don't manage anything, because it means that this alarm is not configured. We're either not using it, well, we're not using it. It's as simple as that. So we have the functionality then to have pre-configured alarms set up on the system, such as high, low, and low alarms for generic analog systems. And should the project require low, high, and high, they can be easily configured just by the fact that they have an alarm present being mapped to it. So this system here is managing the actual acceptance, reset, and the activation of the alarm. So we pass a condition in on our inputs, on our input interface. If that condition goes true, then we set the alarm active flag, which then holds itself on through this system here, this AND gate here, and it also enables us to check this stuff here, which is down here we have our accept all button. If the accept all button is pressed, then because this is an OR gate and our condition is currently active, we accept the alarm. So we can see here our alarm group alarm accepted on our index becomes true, which then holds this on through this contact here. So now we have a alarm condition active and the alarm has been accepted by the operator. If the alarm condition were to go off, our alarm is still active, so our alarm group active is kept on through this system here. So even though our condition's gone off, we're still active, but we've been accepted. And then our structure up here goes through the process of resetting. So as long as we've been accepted, because remember this is an AND gate, so as long as we've been accepted and a reset accepted event has happened, the button's been pressed on SCADA, and as long as our condition is not true, which at the moment it is, it's not true at the moment, this reset flag here, temporary reset flag, is allowed to go to true. When it goes to true, it breaks this hold on contact here, which drops everything else off behind it. So we're no longer accepted and we're no longer active. And that is our sort of complete cycle of raising the alarm when our condition goes true. That enables us to accept the alarm. Once we've accepted the alarm, we're then able to reset the alarm and break that contact of saying the alarm is active. So down here we have our alarm status system, which is part of the sort of global management of the alarm. Again, looking at the individual index, so going back to the structure, which was 3 arrays, this is the 3rd status array. So to begin with, we pass a 0 in to sort of reset it, and then we have a look at generating the statuses here. So this is where our warning plays in. So if we're set to is a warning, then we use these two here. If is warning is not set, then we're using these two here. So we're either passing 1 or 2 or 3 or 4. And 1 is when our alarm is active but has not been accepted. and then 2 is the alarm is active and has been accepted, and it's the same for when we're not set up as a warning, but we pass different values, which would allow us to use different colors to say that this one is not a critical or is a critical, depending on whether it's set up as a warning or not. And then all we do is pass that out as an actual output. So on the switch manager or wherever this global alarm manager is used, we can get a nice, easy, quick view without having to dive into our arrays to have a look at the value there. Quite a lot to take in, but the key things to sort of take away from this are the alarm group is a big structure. There's quite a lot of information on there. I think if we didn't have the statuses, we'd still be passing 128 double words around the system, so 2 lots of 64 double words. And to be moving that amount of information in and out of every single asset that we have in this project would take up a serious amount of CPU time, scan time. There'd be quite a considerable load on the CPU as a result. However, remember back to a previous lesson where we had a look at the differences of inputs and in-outs on interfaces. Passing it via in-out sort of negates that. There's because we're doing it by reference or by pointer, there is no hit on the CPU load as a result of passing it via the in-out. So actually, I'm free to pass this around many objects, as many as alarms we have in groups, and not really feel the strain of having that many. In fact, in other projects, in one that I have the system set up in Siemens tier portal as well. I have 15 groups in a particular project, and I'd say around half of the alarms out of all of those groups are populated. So there's a considerable amount of information there, and I don't have any problems with scan time doing it this way. So it's a really good way of passing alarm information around your project, and when you're ready to add a new alarm to the system, your structure's already there. You simply assign the number and off you go. So before we end the lesson, let's have a quick look at how we do that numbering. If we go back to our inlet system, so here's the alarm number here, so G1_1, which is group 1 alarm index 1. This switch 2 manager is using 2, this quarter turn valve is using 6 and 7, and you'll notice that they are set to, they're assigned from a variable list called alarm constants. The reason you don't want to be using hard-coded sort of 1s, 2s, 6s and 7s on these interfaces is that you can't cross-reference them. So what I actually have in my global data is an alarm constants list, and in this list I simply have all of my variables set as constants. So if I just quickly go offline, it's easier to see. So I have var global constant, which means it's read-only, and I set them up that way. So G10 is our reserved, so there's no comment above it, you're not allowed to use it. And then G11 is my pre-inlet strainer high pressure, G12 is my post-inlet low pressure, and thereon and therein really. And yes, this can be quite tedious to set up. Excuse me, it's easier to set this up from something like Excel with a macro or something like that to generate this for you. Once you get into the habit of doing that sort of stuff, this becomes very simple and easy. And the big benefit is you can cross-reference, which makes it nice and easy to check where this is used or if it's used more than once, because using an alarm index more than once is going to cause issues. So yeah, definitely don't use hard-coded 1s and 0s when it comes to using this approach, because you'll find yourself in a world of issues when you've got sort of 6,000 alarms through your project and you've accidentally used alarm 40 twice. It won't be immediately apparent that you've done that, and it won't be very easy to find where you've done that because you can't cross-reference that hard-coded faulty value that you've used. So hopefully this sort of makes sense. Definitely download this example project and go through it yourself. Go through this lesson again, because this is a concept that is most likely new if you're on this course, and but it's definitely worth having a go at and trying to see the benefits against how you set up your alarm systems now. It does have some real benefits from a CPU load point of view. So yeah, have a go, and if you get stuck with anything, drop me a message, and I'll do my best to sort it out.